Welcome to Math Zone African Motives. Today, we're diving into a powerful new method for solving simultaneous equations. In this video, we will introduce determinants as a tool to solve systems of linear equations. By the end of this tutorial, you will be able to solve a system of two equations with two unknowns using determinants. We'll achieve this by understanding the core concepts of determinants, their notation, and how they relate to the familiar elimination method. Our first objective is to understand what a determinant is and how it's written. This is a fundamental concept in linear algebra. A determinant is essentially an output, a single number, that comes from a specific input, a square matrix. So we take a matrix, a grid of numbers, and apply a rule to it. The single number that comes out is called the determinant. It carries important information about that matrix. You'll most commonly see this notation. We can use the abbreviation det, the capital letter D, or the Greek letter delta. These symbols all mean the same thing. We are calculating the determinant of whatever follows them. Now let's talk about the square matrix. A square matrix is a specific type of matrix where the number of rows and the number of columns are equal. For example, a 2 by 2 matrix has 2 rows and 2 columns, and a 3 by 3 matrix has 3 rows and 3 columns. Our examples today will focus on 2 by 2 matrices. The notation for a 2 by 2 determinant is crucial. Pay close attention to this. Here we have our square matrix A containing the elements A1, B1, A2, and B2. There are two common ways to write this determinant. One way is to write it with the standard square brackets, and the other is with straight vertical bars, like in this example. These vertical bars are a powerful visual signal. They don't mean absolute value. They exclusively mean calculate the determinant of the matrix inside. So, to recap, the determinant is a single number we get from a square matrix. We can write it using the symbols date, D or D, and we use vertical bars or brackets around the matrix to denote the operation. This notation will be our language for the rest of this tutorial. Let's put that notation into practice with our first objective, solving a system of two simultaneous equations using the elimination method, which will lead us directly to determinants. Our goal here is to review the elimination method in a way that builds a foundation for our new technique. We will solve this general system of two linear equations. Remember, the coefficients a, b, and c are just numbers, and our goal is to find the values of the unknowns, x and y. Our strategy is elimination. We want to get rid of one of the variables. Let's start by eliminating y. To do this, we need the coefficients of y to be the same. The simplest way is to multiply the first equation by the coefficient of y from the second equation, which is b2. So we multiply every term in the first equation, a 1x plus b1y equals c1, by b2. This gives us a 1b2 x plus b1 b2y equals c1 b2. We'll call this our new equation 3. Next, we multiply the second equation by the coefficient of y from the first equation, which is b1. We multiply every term in the second equation, a 2x plus b2y equals c2, by b1. This results in a 2b1x plus b2b1y equals c2b1. We'll call this new equation 4. Now, notice that the y terms in our new equations, 3 and 4, are identical. Both equations have the term b1, b2y. This is exactly what we wanted for elimination. Since the y terms have the same sign, we'll subtract equation 4 from equation 3. On the left side, b1, b2y minus b1, b2y is 0, so the y term is eliminated. We are left with a 1b2x minus a2b1x equals c1b2 minus c2b1. Now we just need to solve for x. First, we factor out x on the left side, which gives us x times the quantity, a 1b2 minus a 2b1. This equals the right side, c1b2 minus c2b1. Finally, we isolate x by dividing both sides by the term in the parentheses. So, x equals the quantity, c1b2 minus c2b1, all divided by the quantity a 1b2 minus a 2b1. And there it is. This long, complicated-looking formula for x is a direct result of the elimination method. Notice the denominator, a 1b2 minus a 2b1. This will become very important. If we had chosen to eliminate x instead of y at the beginning, we would have followed an identical procedure and found a similar formula for y. That process would have yielded the solution for y equals a 1c2 minus a 2c1 divided by the exact same denominator as before, a 1b2 minus a 2b1. So we have successfully solved a general system of equations. But look at these formulas. They are repetitive and complex. There must be a simpler way. And there is. The secret lies in the determinant. Now that we've seen the complex result of the elimination method, let's achieve our final objective for this unit: to introduce the 2x2 determinant and connect it to those formulas. We observe that a crucial expression, a 1b2 minus a 2b1, appeared in the denominator of both the x and y solutions. This expression, a 1b2 minus a 2b1, is so fundamental that it has its own special notation. It is called the determinant of the 2x2 matrix made from the coefficients a1, b1, a2, b2. We write it like this, using the vertical bars. You can see how the first column is made of the a coefficients, and the second column is made of the b coefficients from our original equations. The rule to calculate this is to multiply the elements on the main diagonal, a1 and b2, and subtract the product of the elements on the anti-diagonal, a2 and b1. Main diagonal product minus anti-diagonal product. That gives us a 1b2 minus a 2b1. So we can now write our complex fractions using determinants. First, the denominator. The denominator is the determinant of the coefficient matrix. We'll often call this D for the system's determinant. Now let's look at the numerator for x, which was c1b2 minus c2b1. How does this fit the determinant pattern? Let's call the numerator for x d sub x. If we try to write this as a determinant, it must be the determinant of the matrix formed by taking our original coefficient matrix and replacing the x column, the a's, with the constant column, the c's. This gives us the determinant of c1, b1, c2, b2. Calculating this determinant gives us c1, b2 minus c2, b1. It's a perfect match. Similarly, the numerator for y, a 1c2 minus a 2c1, can also be written as a determinant. Let's call this d sub y. This is the determinant of the matrix formed by taking our original coefficient matrix and replacing the y column, the b's, with the constant column, the c's. The determinant of a 1, c1, a 2, c2 is a 1c2 minus a 2c1. Again, it's a perfect match for our formula for the y numerator. And with this, we have unlocked the key to the determinant method for solving simultaneous equations. We now have a much cleaner and simpler way to write our solutions. In this unit, we have achieved all of our learning objectives. We started with the definition and notation of a determinant, solved a general system of equations using elimination, and then, most importantly, connected those solutions to the concept of determinants. You can now see how this powerful tool simplifies the entire process. This method has a name, which we will learn in our next unit.